So I have the utmost pleasure in introducing today's speaker. Evan completed a bachelor's degree followed by a master's at Queen's University in Kingston, Ontario in Canada. Afterwards, he excelled at his PhD at University of British Columbia in Vancouver, pertaining to diamond and mantle research with a focus on unconventional fluid inclusions in diamond. Embarking on more adventures, Evan joined the Gemological Institute of America in New York as at first as a postdoc for a few years and continued on, his work evolving into his current role as a research scientist for the GIA. His primary research focuses on the deep interior of our planet. Its behavior through time is recorded in diamonds, which serve as a remarkable window into the deep earth. Working at the GIA has afforded Evan the incredible opportunity to engage with rare and expensive diamonds not normally accessible for scientific examination. His interaction with these spectacular gemstones have yielded invaluable geologic insights into the earth, since they record mantle processes over billion-year timescales, reflecting otherwise undetectable portions of the carbon cycle and the chemical evolution of the otherwise inaccessible upper mantle. So I'd like to introduce Dr. Evan Smith. He is a lifelong scholar, a great contributor to the diamond world, and also has been a marvelous friend to me for the last 10 years. So please, Evan, the floor is yours.
Wow, thank you so much for that. That's probably the most flattering introduction I've ever had. And thank you for the invitation to speak with you. And thanks for everyone who's tuning in. Good morning, good afternoon, good evening. Maybe it's the middle of the night, wherever you are. But we're all here right now, and that's what matters. So I'm going to talk about how or why the biggest and best diamonds that are recovered around the world kind of defy our efforts initially in exploration. That's the title given here. So I'm currently based out of Vancouver. That's where my home office is, but quite often I'm spending my time in the laboratory in New York. GIA, the Gemological Institute of America, has a lab in New York where a lot of these biggest and best diamonds actually come through for grading purposes. And that's the chance when I get to see them. So as a geologist, you know, why would I be at this place of gemstones? Well, this is the big draw for me, that if you want to study diamonds, you have to go where the diamonds are. And in some cases, that means being among gemstones in their cut and polished form, because that's the only way you get to see them. If you can't buy them or steal them from celebrities and royalty, you have to sort of borrow them and work with the system. So here's a collection of diamonds. These are from Brazil. And just to get you thinking about diamond deposits, I mean, this is sort of a nice collection of diamonds. These are all very high quality diamonds, but you can see there's a big range in shapes, in colors, in sizes. And this is really just the tip of the iceberg in terms of what's out there in variability in diamonds. I think this is one of the hardest things to wrap your head around when you start learning about diamond deposits, is that the diamonds themselves within these deposits can come from vastly different origins, and many different populations can be mixed together and then appear as sort of one population now in a kimberlite or an alluvial deposit. And it's really hard to see those diverse, disparate origins back in time. But they actually become quite relevant when it comes to looking for diamonds or diamond exploration. So where do these diamonds come from? Well, you probably know that most diamonds come from very deep in the earth. At the surface of the earth, the stable form of carbon is graphite. So you need to go much, much deeper into the earth, in excess of 140 kilometers in most places, depending on the geotherm, to get into the diamond stability field. So diamonds form deep in the earth, and most of the diamonds that we recover from mining globally, they grow at depths of about 150 to 200 kilometers deep, and they're brought to surface in kimberlites and related volcanic eruptions, but mostly we're talking about kimberlites in terms of economic primary deposits of diamonds. And these are a couple kimberlites in northern Canada and Northwest Territories. This is the Diavik mine, and these are open pits, and you can see they're kind of spiraling around this central hole, which is the kimberlite deposit itself. But when we see these deposits at surface, just think about how far removed they are from the place where the diamonds grew. If the diamonds grew at depths of 200 kilometers, now they've been completely disaggregated from that setting of formation and brought all the way up to surface. This means that it's really challenging to build a sort of coherent understanding of how and where diamonds form. And building those ideas would obviously be valuable for diamond exploration, but as you'll see, it's quite often difficult to piece together those pieces of the puzzle. So here's an artist's kind of idea of what a kimberlite eruption might look like. As you go deeper into the earth, it's kind of often straight-sided, like a pencil or funnel shaped, kind of like a carrot, but they can also occur in many different shapes like dikes and sills. They can be anywhere from maybe 50 meters to 300 meters in diameter at surface. So they're quite punctuated little targets to be looking for. Now, if you're talking about diamond exploration and your starting point, where would you pick in the world as a kind of go-to place for diamond exploration? The first thing people often talk about is Clifford's rule, or at least Clifford's guideline. And this is the idea that on a global scale, as you can see in this map, diamonds and the diamond-bearing kimberlite eruptions are associated with cratons. They're associated with Precambrian shield areas of continents. So the oldest and thickest parts of continents are where we tend to find diamond deposits. And in this map here, these little diamond shapes are indicating the occurrence of diamonds around the world. And you can see they're within these shaded regions, or at least within these dashed red outlines. These are what we think of as being the oldest kind of cratonic nuclei within the continental lithosphere. And if you made a cross section through some of these continents, it might look something like this. So here's a cross section down into this deepest part of the craton, which we sometimes call the keel, like the keel of a boat. And this is important because this is the region of the lithosphere that's deep enough that it's getting into the diamond stability field, deeper than this dashed line here, which is where you cross over from the graphite stability field to the diamond stability field. So these thickest parts of continents are where the base of the lithospheric mantle stretches into the diamond stability field. And this is the region where we think of most diamonds, say 98% of diamonds growing, and they grow from a fluid phase that might percolate up from the mantle and precipitate carbon in this region. And there are two main host rocks within here. There's this sort of greenish color here, lithospheric mantle, that's usually lherzolite or hartsbergite. So these are largely peridotite kinds of rocks. And then there are these little orange lenses here, and that's basalt sort of composition rock, or eclogite, at these temperatures and pressures. So this is where most diamonds are thought to grow, and then they're brought up to surface by these narrow red lines here. Those are the kimberlite eruptions that we were talking about. So these are both sort of important ideas that we carry in our mind in terms of building a genetic model that can guide us through exploration. Now, a lot of this sort of depth information that we know about diamonds now hasn't always been known. Initially, when people found diamonds in kimberlites, they thought the diamonds had grown as a phenocryst. They had grown from the kimberlite magma. Now we know that's not the case. The diamonds are xenocrysts. So they're some foreign particle, foreign crystal that's been swept up in this kimberlite magma, to which they're not genetically related. So when we look in kimberlites, we find xenoliths from the mantle, chunks of rock from say 150 to 200 kilometers. And those chunks of rock can sometimes have diamonds in them. So we know that those are actually the host of these diamonds. And those chunks of rock have been swept up to surface. And more commonly, those pieces of rock are completely disaggregated and the diamonds occur as xenocrysts. And when we have isolated diamonds, quite often they have inclusions in them that make a great sort of sample to study, to understand how diamonds grow. When we look inside diamonds, we see things like this. We see inclusions. And the inclusions are other mineral grains that were enveloped in the diamond as it grew at, say, a depth of 150 to 200 kilometers. This diamond encased a little grain of olivine, or this diamond enclosed a grain of kyanite, and this orange almandine pyrope garnet. So in this case, the host rock is probably an eclogite. In this case, the host rock is probably a peridotite. And we've learned a lot from studying both diamond-bearing xenoliths and the inclusions within diamonds. Here are some more examples of these inclusions within diamonds. Again, here's an orange garnet indicating this diamond probably grew in a host rock that was eclogite. And here are a couple other inclusions that probably grew in a peridotite host rock. There's a reddish, purplish kind of peridotitic chrome-rich pyrope garnet, and a chrome-rich clinopyroxene over here. That's this bright green color. Now, the inclusions become extremely relevant for exploration because these are the grains that are trapped inside the diamond. But if you think about all the grains that have been disaggregated from those mantle rocks, the xenoliths that have broken apart, those other grains not trapped inside the diamond, but that were neighboring to the diamond, are going to be much more abundant than the diamonds themselves. Those are indicator minerals. So when we're looking for diamond deposits, a lot of energy is put into not searching for the diamonds themselves, but into searching for kimberlite indicator minerals. So these are mineral grains that are related to the diamond formation. So again, a diamond might have formed here and it's surrounded by thousands of grains down in the mantle that might be swept up along with the diamond and be much more abundant than the diamond, but still be indicative of that kind of region in the mantle that's prospective for diamonds. So these kimberlite indicator minerals, like this colorful collection here, so again, we've got purple chrome-rich pyrope garnets. We've got some other reddish garnets and orange garnets from, these would be from eclogites. We've got some chrome-rich pyroxenes here, clinopyroxenes, and spinels and ilmenites. And we can see that these little indicator minerals are mirrored by the inclusions that we see in diamonds. They sort of go hand in hand, which is sort of what's given us this confidence in using indicator minerals to search for diamonds. Again, they're transported along with the diamonds, but they're more abundant than the diamonds themselves. So indicator minerals are a big tool for diamond exploration. Here's another shot of some indicator minerals, and we can just point out the major ones here. The chrome pyrope garnets are these purple ones. Chrome spinels or magnesiochromites are these black ones. Quite often they can have a octahedral crystal shape. And there's the bright green chrome diopsides. And in cooler locations where olivine doesn't break down, sometimes olivine itself can be a valuable indicator mineral. One other one I'll point out is ilmenite. So ilmenite is something that appears again within the sort of mantle package where we would expect a lot of diamonds to be growing. Ilmenite's actually part of the megacryst suite. So sometimes these ilmenites can be quite large. When you find them in the kimberlite, they can be in excess of 1 centimeter. You can have these large ilmenite grains. But looking for all of these grains is a great way to look for diamonds by proxy. So this map here over on the right shows a very simple and very successful, I guess, example, just to get you thinking about how this might work. So this is a region in Ontario near Temiskaming. This is sort of northern or central Ontario. And this region has been glaciated. So the material, so you'd be sampling sediments. In this case, you're sampling glacial till or glacial esker deposits. So these are pieces of rock and grains that have been sort of swept up from their original location and transported by glaciers. So you really need to understand the glacial history in this region to sort of backtrack where all of this material has come from. So that's what's shown here with these arrows. In this region, there's been two big directions of ice flow, and their sum is sort of broadly southward in this region. And all of these dots are places where glacial till has been sampled, and the sample has been sorted for particle size and for density. So these are heavy minerals. And then these indicator minerals have been picked out under a microscope by hand. And that's what this plot is based on. So all of these samples have now been counted for their indicator mineral content. And the larger the circle, the more indicator minerals are in there. And the colors correspond to which indicator minerals are there. So a lot of these big circles are gray because they're actually dominated by ilmenite. So here you've got this map now showing where the indicator minerals are. You know that the direction of transport has been to the south, so you can track back this big hot spot of all these ilmenite grains farther and farther north until it stops. There's nothing more up here. And this actually corresponds with the location of two kimberlites where all of these ilmenites and these garnets associated with them have actually been sourced. And it's important to note that there are actually some other kimberlites here, these little yellow diamonds off to the side, that haven't really generated any kind of an indicator mineral train. And that's because they're probably more deeply weathered. So they just aren't shedding the same load of kimberlite indicator minerals. So that's just sort of cautionary note that not all kimberlites are going to be associated with these kimberlite indicator mineral trains. But anyway, so when it comes to diamond exploration, it's sometimes referred to as a needle in a haystack kind of operation. But in reality, it's much more complicated than that, because you have to not only find a haystack, but many of the haystacks that you find don't actually contain a needle. So diamond exploration is about finding kimberlites. And a big tool here is using geophysics to sort of pick up on their extreme contrast in magnetic resistivity and density compared to the surrounding country rocks. So kimberlites really stand out as an anomaly in some of these geophysical methods. And we also use indicator minerals. So both of these techniques allow us to vector towards a kimberlite, and also a kimberlite that has some kind of a mantle payload from that rich region that we want between 150 to 200 kilometers. We want the kimberlite to have a lot of material sampled from that mantle region. And this assessment of the mantle payload is really relying heavily on this idea of peridiotic and eclogitic diamonds from the lithospheric mantle. Another piece of information that's sometimes used in exploration is the assessment of microdiamonds. So now you've got a kimberlite. It's got lots of kimberlite indicator minerals, so you think it might have sampled a lot of this sort of mantle material we want. Now you can take a sample of kimberlite and digest it in hydrofluoric acid, or use caustic fusion to sort of dissolve everything that's not diamond and just be left with all the diamonds in that sample. The benefit here is that there are many, many more small diamonds than there are big diamonds. So you can use the small diamonds in a more modest sample of kilograms to get an idea of how many diamonds are sort of in this kimberlite. If you have a lot of micro diamonds, that's usually seen as a good sign. And the micro diamonds are sometimes used as a preliminary indicator of the size frequency distribution to sort of extrapolate out to the macro diamond population. So things that are larger than 0.5 millimeter or 1 millimeter, how abundant might they be? Well, you can get an idea from studying micro diamonds, even though the micro diamonds, we are pretty sure that they are sort of genetically distinct from the macro diamonds. So they are found together and the system kind of works, but we know that they're not the same beast. They're not the same diamonds, bringing us back to that idea that all the diamonds we see in the deposit haven't formed in exactly the same way. It's sort of a mixture of diamonds from diverse origins. And that brings us to the biggest and best diamonds. The problem that we have in exploration and then even in mining is that these factors that we're using, especially the indicator minerals and even the micro diamonds, these proxies for diamond grade and value really don't correlate at all with the biggest and best diamonds. And what I mean by the biggest and best diamonds is diamonds like these. So diamonds that are bigger than 10 carats or 100 carats. These diamonds have distinct characteristics and quite often are worth a lot more money, not simply because they're a big diamond, but also because they tend to be higher in their color and their clarity. And this makes their per carat value quite higher. So these diamonds are a real desirable feature to have in any diamond deposit. Now, the theme that I'm talking about today is largely inspired by this abstract from the 2012 KIMBERLITE conference. It was submitted by the late John Gurney and his longtime collaborator, Herb Helmstead. And this abstract is about type 2A diamonds, which you'll see is sort of the kinds of diamonds that we're going to be talking about, and their enhanced economic significance. And there are 3 points I want to draw from this abstract. The first point that they go at length to try to illustrate is that these diamonds are distinct from other kinds of diamonds. They're not just bigger or better clarity or color. They actually seem to have a complete set of characteristics that would suggest they're genetically distinct. They formed in a different way, but they're extremely important because just having one of these diamonds, say one diamond over 20 carats with this sort of set of characteristics, a 120 carat type 2A diamond in a package of 50,000 tons of rock can convert to a revenue in excess of $20 per ton. So can you imagine that if you had a mine where you had to mine, 10,000, 20,000, all the way up to 50,000 tons of material before you switch over from being completely uneconomic to being profitable? That's sort of the problem that we're getting at here. And these diamonds that can be a mine maker are difficult to work with because the only way to predict the presence, size, and abundance of these crystals is to take a very large bulk sample. So what we're saying is the kimberlite indicator minerals really don't work for these diamonds, and you have to just look for the diamonds themselves. You have to take a bulk sample. Upwards of 100,000 tons is not out of the question. And you can see these diamonds kind of expressed in this plot here. So this is a plot of many different diamond mines. So these are sort of economic kimberlite, diamondiferous kimberlite deposits from around the world, as well as one lamproite. This is the Argyle diamond mine in Australia. And they're put here in terms of their diamond grade and the value of the diamonds, value in dollars per carat. 1 carat is 0.2 grams. The value per carat, you can see there's quite a spread. You have some diamond mines that have a very high grade, but the diamonds you're recovering are very low value. And at the opposite end of the spectrum, you have some diamond mines like Letseng in Lesotho is a great example of a diamond mine with extremely low grade, but a lot of the diamonds that are recovered there are these type 2 diamonds that have extremely high value that makes this diamond mine profitable. So 80 or 85% of the revenue from this diamond mine is coming from these sort of enigmatic kinds of diamonds. So let's go back and talk about diamond genesis here. We sort of hinted at this idea that there are many different ways diamonds form in the mantle, different in terms of the depth or the host rock or the melt or fluid involved in those diamonds forming. And there are multiple known perigeneses. So we have diamonds forming in eclogitic and peridotite host rocks in the lithospheric mantle, for instance. Again, this accounts for, we think, maybe 98% of the diamonds recovered globally. But what we're going to talk about now are two particular enigmatic varieties that constitute these biggest and best diamonds that I got at in the title. The first is boron bearing or type 2B diamonds. And a perfect example of this kind of diamond is the Hope diamond, which is on display in Washington, D.C. at the Smithsonian. And the other kind of diamond are these things that we were loosely calling type 2A diamonds, but now we have a name for them. We call them clipper diamonds. And the perfect example of diamonds like these would be the Cullinan diamond. This is the largest gem diamond ever recovered. It was 3,107 carats. And this is the largest piece cut from it, the Cullinan 1, which is now on this scepter in the collection in London. This is part of the crown jewels. So I mentioned this idea of diamond type, and I should just define that quickly, what that is. Diamonds sort of come in two flavors, you could say, when it comes to spectroscopy. Infrared spectroscopy can detect the presence of nitrogen in the diamond crystal structure. And when you have nitrogen in the diamond crystal structure, that's a type 1 diamond, and that constitutes about 98% of diamonds. And type 2 diamonds are diamonds where when you do infrared spectroscopy, you don't really see any nitrogen at all. And the simplest case is one where it just looks like it's carbon. That's a type 2A. If you also have absorption due to boron impurities in the crystal lattice, that's our type 2B example. So to illustrate how these diamonds sort of manifest themselves within the marketplace, where we have millions of diamonds to look at, we can look at diamonds and sort of distribute them by size to see how these diamonds manifest themselves. So here are 3 histograms in 3 different size categories. So these are taken from a population of 3.5 million diamonds. And if you look at all the diamonds that are smaller than 1 carat and distribute them by color, so this is the GIA color scale going from perfectly colorless, D color, all the way out to slightly yellowish or brownish colors into J, K, and L. So in the small diamonds, you got a hump around F color. And as you look at bigger diamonds, 1 to 2 carats or 2 to 3 carats, that hump moves over to the right because the diamonds are bigger. So you've got more volume for the light to pass through and more light gets absorbed. So it makes sense that this hump would move over and you would see more and more color pronounced in the cut diamond. And if you look at slightly bigger diamonds, say 5 to 10 carats, this hump goes even farther to the right. And if you go larger, 10 to 20 carats, the hump is still moving, but look at this. You've got this huge explosion of perfectly colorless diamonds. All of a sudden, you've got lots of D-colored diamonds. And if you go to bigger diamonds, bigger than 20 carats, this sort of dominates the histogram now. You've got lots and lots of diamonds that are perfectly colorless. And what these diamonds are these type 2A diamonds, or clipper diamonds, as we'll call them in a moment. So here's that sample of 3.5 million diamonds. You can see very few of them are type 2. Very few of them have no nitrogen. But when you look at the largest diamonds in that population of 3.5 million, the largest 1,000, 500, 100, or largest 50, the proportion of type 2 diamonds skyrockets all the way up to 50%. So these diamonds aren't just low in nitrogen, they're also very markedly skewed towards very large sizes. And you can see that they also have a difference in their clarity or their inclusion content. So here we've taken that bracket of largest 1,000 diamonds and separated them into type 1s and type 2s. And down at the bottom, this is the clarity scale. So I3, I2, I1, all the way up to very slightly included and internally flawless and perfectly flawless. So moving towards the right, you have fewer inclusions in the diamonds. And you can see that the type 2s are again skewed over to the right. So suddenly this isn't just about nitrogen, this is about size, this is about clarity. And we'll see it's also about surface textures in the rough diamonds too. So here are a set of these type 2A diamonds from the Letsang mine, which is known for these kinds of diamonds. And again, you can see these diamonds in their rough form kind of stand out from what we typically see in rough diamonds. These are always irregular in shape rather than nice crystal shapes. They're skewed to the large size range. They're inclusion poor, and the surface textures are extremely resorbed. So you don't really see any pristine crystal faces. Everything has been dissolved and kind of chemically attacked by some process of prolonged dissolution in the mantle. And this is very different from what we see in other kinds of diamonds. So everything we see suggests that these are a distinct kind of type 2A diamond. And if we recognize all of those characteristics together, that's where this acronym CLIPPER comes from. So this population of diamonds, which now we're going to call Clipper diamonds, that make up many of the world's biggest and best diamonds. They're Cullinan-like, so they're sort of tied to the type example of the Cullinan diamond. They're large, inclusion poor, pure, irregular in shape, and resorbed. Now, they're inclusion poor, but sometimes black inclusions have been noted. Black inclusions like these in this large diamond from the Williamson mine, or this, which is a window cut into a famous diamond called the Lesotho Promise. And you can see these black things. They look almost like a flake of graphite. And for many years, that's what people thought they were. But this is sort of the problem that drew me to GIA to pursue my postdoc. I really wanted to see some of these high quality gem diamonds and get to the bottom of this problem. What are these little inclusions in here? Again, if you're at a university, it's really difficult to just buy multi-million-dollar diamonds for research. So the only way to really tackle this problem is to go where the diamonds are. So I began this search for inclusions. I was at the GIA looking for type 2A and type 2B diamonds with inclusions. And I had the advantage of being able to borrow diamonds from the grading operations. So every year there are millions of diamonds coming through this global infrastructure of laboratories that has the capability of sort of picking out some of these diamonds that would otherwise be extremely rare occurrences. So if you want to study rare diamonds, a place like this that sees millions of diamonds is a great place to go, because these rare examples are popping up with some regularity. I was also able to obtain some offcuts. So when diamonds like this are being cut and polished, sometimes pieces are trimmed off, and I was able to obtain some of those more heavily included regions of the diamond to study. So I have examined 83 of these type 2A or Clipper diamonds and 46 type 2B diamonds using a variety of methods, mostly Raman spectroscopy because it's non-destructive. So you can aim a laser down a microscope at one of these little inclusions, gain some information about what that inclusion is made of, and you haven't destroyed the sample at all. You can still give it back at the end of the day. So that's a hugely powerful, non-destructive technique. And the results from studying all these diamonds has really unraveled the geological origin of diamonds like these blue ones and these big and D color Clipper diamonds. So back to this population of Clipper diamonds, what are the inclusions inside them? Well, many of them are actually metallic inclusions. So to the eye, you would see this big black flake, but under higher magnification, you can see that many of these black flakes that look like graphite actually have an inclusion nucleus to them. They have a real solid volume that's sort of masked, but it's in there. And this material is actually present in the majority of these diamonds when they have inclusions. So here's a whole bunch of examples of some of these Clipper diamonds containing metallic inclusions. And they're metallic in the sense that they look metallic. Their luster is very reflective, but also in their composition. So in the next slide, I'm going to cut through one of these inclusions, and you can see what it looks like inside. This is a false color map showing different elements. So iron is in green, nickel is in pink, and sulfur is in this more turquoisey blue color. And this is one of these inclusions cut through the middle. And you can see immediately that it's not just one mineral inclusion. There are multiple phases here. There are three main phases. This sort of iron nickel alloy, this bright green iron-rich phase, which is actually it's an iron carbide. And here where you've got the sulfur, this is iron sulfide, it's pyrrhotite. Now, this is, again, something that was very prevalent among the diamonds I looked at. 67 of the 83 diamonds have inclusions like this. And if you were to take this assemblage and bring it back down to mantle pressures and temperatures, it would be a melt. So these are really melt inclusions. They're liquid metal inclusions. And these likely represent what the diamond grew from. So we think that this is probably the growth medium for these diamonds, which immediately sets them apart from other kinds of diamonds that we know don't grow from metals in nature. So these are kind of unusual. Now, they also contain some other kinds of inclusions. 23 of those 83 samples had examples of majoritic garnet or this calcium silicate, which is now in a lower pressure phase, but the interpretation is that it was originally trapped in the perovskite crystal structure. And these are minerals that only form at extreme pressures. And they tell us that these diamonds are likely derived from depths of 360 to 750 kilometers deep in the earth, which is several times deeper than those more common diamonds formed in the lithosphere. So these diamonds are super deep diamonds. Now, those minerals that I mentioned, you can plot them up here on these two charts. So here are two major rock types in the mantle. First, we've got peridotites, and the other is basaltic kind of composition, like the ocean crust. And this shows the main minerals that make up those rocks. As you go deeper and deeper into the earth and the pressure and temperature increases, some minerals disappear, some new minerals appear as a function of pressure and temperature. And we can plot up where these majoritic garnets and the calcium silicate phases fit. You can see that they sort of overlap with minerals we expect to be appearing in the transition zone or down into the lower mantle. Now, one new mineral that I've observed recently in Clipper diamonds is this orange phase here, which is bridgemanite. So I'll show you this diamond because I was quite excited about it. I just found it a few months ago. This is the diamond here. It's a 124 karat diamond. So that's about the size of a walnut maybe. And it's relatively fractured and inclusion bearing. So it looks pretty ratty. It doesn't really look like the biggest and best diamonds out there, but it definitely has all the right characteristics to belong to this population. And in detail, this still has very large regions within it that are of colorless top gem quality. But this rough diamond, even in its rough state, you could see some inclusions just below the surface. So here's a group of little tiny inclusions. I'll point them out there. And this cluster of 9 related inclusions, I was able to identify them again with Raman spectroscopy, so non-destructive. And the minerals represented here are orthopyroxene, spinel, something called jeffbenite. And together, these actually form an assemblage of aluminum-bearing bridgemanite, which is the magnesium silicate perovskite phase of the lower mantle. So this gives us a little bit more confidence in placing that depth bracket for Clipper diamonds. And if we make a geological picture of how these diamonds form, we know that they're forming very deep in the earth, and they're forming in the presence of some kind of a liquid metal that we think they're growing out of. And then these diamonds eventually are making their way up to shallower depths where they're entrained in a kimberlite eruption. And then we see them at surface mixed together with all these other shallower diamonds here. Now, we'll keep moving into type 2B diamonds, which are again, sort of the cousin to these Clipper diamonds, the cousin that contains boron. So these diamonds are also nitrogen free, but they're characterized by the presence of boron, which can be there in amounts from 0.01 all the way up to 1 or 10 ppm within the crystal structure. And this boron can sometimes give them a really nice blue color, like the Hope diamond. Now, they're very rare globally. They make up much less than 1% of mined diamonds, but they still have a global footprint. And these blue diamond symbols here show some of the major locations around the world where diamonds like these have been found. And they're interesting from a geological perspective because boron is a quintessential crustal element. We find lots of boron at the surface of the Earth because it fractionates strongly into melts and then gets re-enriched in any kind of water circulating near the surface of the Earth. So there's lots of boron in evaporite deposits, but very little boron in the mantle. So people have really wanted to know why these diamonds have this boron and where it comes from. And now, again, the problem is looking for inclusions. So being at the GIA and being able to look at a lot of diamonds like this allowed me to put together a picture of the sort of inclusions within these diamonds by sampling thousands and thousands of diamonds and picking out the few examples that still have their inclusions intact within them. And the inclusions we see in these type 2B diamonds are, again, high pressure or super deep kinds of minerals. We have examples of bridgmanite, calcium silicate perovskite, stishovite, majorite, this calcium ferrite type phase, ferropericlase, and 16 of these diamonds, 16 of the 46 diamonds have former bridgmanite, which again is that lower mantle magnesium silicate phase, indicating a depth of origin from the lower mantle beyond about 660 kilometers. We'll go back to this lovely plot here and point out just some of those minerals. So we've got the calcium silicate perovskite phase. Here's one of those inclusions. Also got bridgmanite, ferropericlase, stishovite, and this phase here, which is got a lot of sodium and potassium in it and aluminum. It's a sort of minor phase, but it's really important because it indicates an origin from basaltic host rocks at lower mantle depths. So the assemblage of inclusions that we see in type 2B diamonds, put in all together, we've got examples of both peridotite and basaltic kinds of rocks at depths corresponding to the transition zone or lower mantle. And the interpretation here is that this represents the mineralogy of a subducted oceanic slab with its crust and attached lithospheric mantle that has now been subducted to the transition zone or lower mantle depths. And this immediately suggests that these host rocks, because they're subducted, they might bring boron with them from the surface of the Earth down deeper into the Earth where these diamonds crystallize. And we think that one of the most prospective vehicles that could be carrying this boron would be serpentinized rocks, particularly the serpentinized peridotite, the mantle portion of that oceanic lithosphere just under the oceanic crust. So this boron might be recycled with serpentinized oceanic lithospheric slabs being subducted down to the lower mantle. So if we put all of these ideas together now into one sort of geological picture, this is what it might look like. So we've got the continental lithosphere and these thickest parts at depths of 150 to 200 kilometers. This is where most diamonds we are mining that are profitable, where they come from, depths of about 150 to 200 kilometers in the lithospheric mantle. And these are associated with lithospheric mantle xenoliths and xenocrysts, which form the indicator minerals that we're using as a vector to find prospective kimberlites with big mantle payloads from the mantle lithosphere that might correspond to these diamonds. And then down below that, hundreds of kilometers away in a completely different part of the mantle, this is where some of these biggest and best diamonds are forming. We've got clipper diamonds that are formed in association with this unusual iron and nickel rich metallic liquid. And then we've also got these type 2B diamonds, the boron bearing diamonds, that seem to be forming again at depths of the lower mantle or transition zone and are associated again with these subducted oceanic lithospheric slabs. And we think that these slabs might be contributing boron to these diamonds. And they also probably contribute carbon because a lot of the carbon isotopes that we see in these clipper diamonds and type 2B diamonds are a range of carbon isotopes from very light to more moderately heavy carbon isotopes, as opposed to the more narrow range that we think of as representing the ambient carbon within the convecting mantle. So the carbon isotopic signatures also sort of play hand in hand with this idea of subduction being very important for the formation of these diamonds. So this sort of is the explanation of why these biggest and best diamonds kind of don't correlate with our traditional indicator minerals or the micro diamonds that we're looking at that probably formed in this shallower environment here. They're just so far removed, even though now we find them together in some of the same deposits. So what we've seen largely from studying inclusions in large gem quality faceted diamonds is that these clipper diamonds, or more loosely type 2A diamonds, and type 2B diamonds, the boron bearing ones, these are sublithospheric or super deep diamonds. And in terms of their genesis, they are distinct from lithospheric or cratonic diamonds. And this is the reason why they don't correlate with the lithospheric indicator minerals like the chrome pyrope or chrome spinels or the chrome diopsides or the ilmenites. And they also don't correlate with other diamond populations in the same pipe. So they can be extremely difficult to predict whether or not they're there, how many there are, but they're extremely important to the economic viability of diamond deposits where they do occur. Now, because we've got some idea now of how these diamonds form, I think this is a really good jumping point. These are some really good clues to help us investigate non-traditional tools for diamond exploration. And the two big things that we've learned is that these are sublithospheric diamonds. So maybe we should be looking for sublithospheric, some kind of geochemical signature. I'm not saying I know what that is, but this is where we should be looking. And the signature we should be looking for probably has something to do with deeply recycled slabs, perhaps deeply recycled slabs that have been serpentinized and have lost some kind of volatile budget in some episode as they've reached the lower mantle. And that episode has triggered a diamond formation. And maybe there are some hints of this kind of diamond formation that preserve all the way up to surface. Now, some good places to look to try to find out what some of these indicators might be, if they exist at all, would be to look at diamond deposits where we find a lot of these diamonds. And that's deposits like Letseng, the Karoi mine, Cullinan mine, Coffee Fontaine. And these are mines that could serve as potential type localities for us to try to suss out some potential indicator for these diamonds. Currently, they do defy exploration, but as we've seen in the last many decades of diamond exploration, the more we learn about how diamonds form, the more tools we uncover. So maybe now some of these new clues about how these diamonds form and where they form might lead us to some prospective new tools for diamond exploration that could help us home in on some of these biggest and best high value diamonds that are out there. Maybe we've overlooked some and we don't want to do that. So that's all I wanted to talk about. And I think now we can open it up for some questions and discussion.
Yeah, thank you, Evan. That was pretty fascinating. I mean, if anything, these are just beautiful photos, and especially the mineral inclusions that you showed at the beginning. I found those very nice to look at. Yeah, so while so Evan, if you just leave up this slide, we can.
Sure.
And then yeah, so we'll have the way the questions work. I think everyone knows the formula, but I was just gonna, before people start asking questions and get themselves ready, I just wanted to ask you, because you mentioned that sometimes you find like you found a diamond a couple months ago and sometimes you get offcuts. Like what exactly is entailed in that? Are you, like, do they say, okay, you have 5 minutes to rummage around here, or yeah, how does that process work?
Yeah, so most of the diamonds that I get to see have been submitted to the laboratory in order to get a certificate that says, you know, this is the cut, clarity, carat weight, and color of this diamond. So it's going through the laboratory, it's visiting a few different people and instruments, and along that pathway, I might be able to borrow it for hours or maybe even a couple of days if I'm lucky, and then I have to give that diamond back. So that would be the most common example. Some of these other examples where I said, yeah, an offcut, this is much more rare. I've really only seen a few of these, and it requires having the right connections, being able to find someone who has perhaps bought one of these diamonds and is in the process of cutting and polishing it and is willing to take the time to listen to your questions and willing to play along with you, because really for them to take the extra time and care to trim off some inclusion bearing piece and bring it to you doesn't really translate into dollars for them. So it can be difficult to source off-cut samples like that. And the rough diamonds, that's something I've only ever seen a few examples of when they're submitted sometimes as rough diamonds to GIA to sort of catalog their features, either as part of a story that's going to track this diamond from rough to all the different steps of polishing and faceting all the way to a finished product, or they've been submitted as rough as a part of the new diamond origin service that GIA has. So the rough diamond will be cataloged and described in detail in order to match it up with its faceted counterpart once it's done. And that gives a lot more confidence to sort of from beginning to finish, from beginning to end, to say that this rough diamond is actually the starting point of this diamond. And we know that rough diamond came from mine X. So we know this polished finished product came from mine X as well. So we have a lot of confidence about the diamond origin.
Mm-hmm. All right, pretty interesting. The questions are rolling in. The first one is actually gonna go to Luis Chambel. I'm gonna unmute you. You're welcome to ask your question directly, or I will ask it for him. It says, any age difference between the common diamond population and the clipper? And then a second follow-up question is, do you have any data on the Lulo diamonds from Angola?
Okay, yeah, I mean, those are really great questions. Unfortunately, we don't really know how old these diamonds are, the clipper diamonds or type 2B diamonds, how old they are in relation to some of the other more common diamonds from the lithosphere, or how old they might be in comparison to some of the other examples of sublithospheric diamonds, because there are some diamonds, for instance, from Brazil that are sublithospheric in origin, but they're much, much smaller and very poor gem quality. But we don't know how all of these different populations relate in terms of age. And the reason we don't really know the age for these clipper diamonds is that we don't have good inclusions to study in terms of the some kind of a radiometric decay system that would give us an idea, oh, these diamonds are X age. So they might be around the same age as the kimberlite they're hosted in, or they might be much older by many millions of years. We just don't know. And the diamonds from Angola, from the Lulo deposit, I've only seen a couple examples of those. So I really can't speak to how they relate to the rest of these populations, but certainly their characteristics are comparable, and they seem to be part of this same population with the clarity and the color and the morphology of these clipper diamond populations. You can really see that well in the 404 carat diamond that was found a few years back from the Lulo deposit. That is definitely one of these diamonds.
All right, thanks. Aaron, could you grab the next question?
Sure. No, thanks again for the brilliant talk, Evan. tons of questions, so I'm just going to get right into it. I'll let Gaurav Agrawal ask his question, and then we'll follow that up with a question from Holly that's about similar topic. Gaurav, I hope I'm saying your name right, but I've unmuted you if you'd like to ask. Okay, well, while I figure out how to unmute Gaurav, I'll ask Holly's question, which is, why would the carbon nickel iron rich melt form, and why only once it's reached this sort of lower transition zone?
Yeah, so the origin of that metallic melt is something that we're still investigating. And the leading idea that we had sort of a couple years ago was that it's related to disproportionation. So deeper in the mantle, below a depth of about 250 kilometers, even just peridotite, as you take them deeper and deeper, some of the minerals like garnet especially will have more and more room in their crystal structure for iron 3+. And the capacity to store iron 3+ becomes greater and greater, to the point where some of the iron 2+ will disproportionate. So the iron 2+ will become iron 3+ and iron 0, native iron. So the charge as a sum hasn't changed, but you've got some iron that's sort of been oxidized and some iron that's been reduced. And the reason for this is just because of mineral physics, because the garnets and other minerals deeper down have more and more capacity to host iron 3+. So as you go below about 250 kilometers, the ability for minerals to take up iron 3+ sort of dictates that some native iron is expelled due to disproportionation. So the rocks actually become reduced all on their own, even without any kind of external chemical reactions. The rocks become more and more reduced to the point where native iron exsolves. And once you have native iron exsolving, nickel goes with it. Sulfur should also kind of partition into it. Carbon goes into, all of a sudden, all these things start partitioning into that metal phase. And that's sort of the leading idea as to how you would get metal at these depths. But we don't know for sure that that's where the metal's coming from, because it's so closely associated with these subducting slabs. It suggests that the story is actually a bit more complicated than that. And this is something that we're continuing to explore, exactly how the metal comes to be and what its fate might be, aside from the diamonds that we think crystallize from it.
Oh, that's, yeah, no, I think that's a really good description. And then the carbon goes with that. I think maybe I'm not understanding why.
Oh, yeah. So there's lots of carbon in the mantle, and carbon is present in most fluids and melts, like low degree partial melts and fluids are quite often carbonatitic in composition if they're low degree melts derived from the mantle. So there's carbon around, and if you had a phase like this metallic iron kind of liquid phase, it has a very high solubility for carbon as well. So if there's carbon in this environment and you have an iron nickel rich metallic liquid, it has a very high ability to dissolve carbon. And then if you fluctuate the temperature or pressure or the composition of that metallic melt, you could drive that carbon to supersaturation. So now this melt that contains a lot of carbon loses some of its ability to hold carbon and starts precipitating pure carbon as diamond. And this is actually the way that most industrial synthetic diamonds are grown. They're grown in a high pressure, high temperature vessel that's full of iron and nickel or cobalt, and they dissolve graphite into it. And then by controlling the temperature gradient, they actually precipitate diamond out of this metallic flux. So it's really interesting to see that nature is doing something similar.
Yeah, no, this is exactly what Gaurav's question was about. Is this liquid metallic inclusions you find? Is this basically what they're growing in the CVD lab grown diamonds?
So the diamonds that we're talking about for the lab-grown diamonds are HPHT synthetics, not CVD synthetics. CVD synthetics are grown from almost in a vacuum by a ball of plasma. The diamonds that are grown in this metallic liquid are called HPHT synthetic diamonds. And the little inclusions that you see sometimes in synthetic diamonds look broadly similar to some of the ones that we see in these natural diamonds. But the natural diamonds, the inclusions that we see have sulfur in them, which is actually quite different. And they also don't have cobalt, and they have a different ratio of iron to nickel. And the natural inclusions also have a much different morphology to their inclusions. And in the natural diamonds, the inclusions have quite often ruptured some of the surrounding diamonds. So you have these large graphitic fracture halos around the inclusions, which is something you don't see in the synthetic diamonds.
Right. You mentioned something about the carbon, like how there's actually a ton of carbon down in the mantle. And so we have a question from Alana, and she'd like to know what is the mechanism to focus carbon from the melt enough to form the type 2 diamonds in general?
Yeah, I mean, up front, I guess we don't have a great understanding of exactly how any diamonds form, but the prevailing idea is that you've got some kind of a melt or a fluid that has carbon dissolved in it, and it's a very low degree melt or fluid, sort of percolating along grain boundaries or maybe migrating along small veins. And it's sort of this evolution of this fluid, either as a function of pressure or temperature, or its changing composition as it migrates through these rocks, that causes the carbon that's dissolved within it to reach supersaturation and start coming out of solution. So exactly what triggers that, we don't really know.
All right, it just adds, I guess, to the mystery of, the mantle, basically. So I guess the next question we're going to try to, Jose has a pretty interesting question. I'm going to try to see if we can get him to unmute, but you're free to ask your question.
Hi, Evan. Congrats for the presentation. It's very interesting. My question came from, usually you found the type 2 diamonds or clipper diamonds together with very low quality diamonds. There is genetic relation between the very low quality diamonds with that top quality diamonds, giant diamonds?
I'm not sure I quite understand the question. The association between these lower quality diamonds and
because they occur in the normally when you found the big diamonds and the top quality diamonds, type 2A diamonds, you also found in the same spot very low quality diamonds. There any genetic relationship between those two types of diamonds?
Not that we know of. I mean, it seems that every place where we've found these clipper diamonds in every deposit worldwide, there are other kinds of diamonds associated with them. Even in a mine like Letseng, where they have lots and lots of these clipper diamonds, they also have diamonds from the lithosphere, and they also have indicator minerals there too. So it's really hard to piece together all these diverse origins when you're looking at a single deposit. Everything's all kind of mixed together. But as far as I know, some of the lower quality, more heavily included or smaller diamonds in any deposit haven't really been connected in a genetic sense with the clipper diamonds or the type 2B diamonds.
Thanks, Evan. And thanks, Jose, as well. The next question we'll get Herman Grutter on.
Hi, Evan. Great talk.
Thank you.
I have a technical question which relates to these decomposed ultra deep phases. Do you have an idea at which depth range their decomposition products are actually are crystallizing out. In other words, if they come from 650 kilometers, are we seeing that high pressure phase destabilize at say 200 kilometer depth?
Yeah. Here, let me go back to one of these images here. So for instance, yeah, this inclusion here sort of gets at the question. So you can see that it's not just one phase here. You've got a colorless region and this black region. So the question is pertaining to a lot of these inclusions, they're trapped as one mineral, but then at some point on their way to surface, they exsolve into, they destabilize. They're not stable anymore because the pressure is being relieved, and you find quite often an assemblage of lower pressure minerals that we then interpret as that original high pressure phase. And the depth at which this sort of separation into lower pressure minerals forms, I don't think that we have a great idea of that, but for some diamonds, it looks like it's happened at a matter of hundreds of kilometers. For instance, calcium silicate perovskite, that we think is calcium silicate perovskite, is sometimes separated into an assemblage of calcium silicate in the titanite structure and something else called larnite, which is almost like an olivine, but the magnesium and iron is substituted with calcium. So those two different minerals together that we interpret as calcium silicate perovskite, those two minerals would probably have exsolved at a depth of like 10 gigapascals, so like, 300 kilometers or something like that, as opposed to breaking down, within the kimberlite. But this is probably something that could be investigated further to get at some kind of idea of how quickly the diamonds have been brought up to surface. In some instances, it seems like they've been brought up very quickly, and we have examples of high pressure minerals that are preserved in their high pressure structure, like ringwoodite. There's been one great example of ringwoodite documented in a diamond. And ringwoodite is the high pressure analog of olivine, and it's very susceptible to decomposing down to the lower pressure olivine crystal structure. To preserve it as ringwoodite requires some kind of an ascent speed to sort of get the right kinetic story happening to preserve ringwoodite. So at what depth these sort of back transformations, these retrogressions happen, I think in many cases it looks like it's hundreds of kilometers depth. Does that answer the question? I forget.
Yeah.
Yeah. Okay, thanks, Evan.
Thanks a lot, Evan. We have a question even from our YouTube viewers, from Richard Redfern. He asks about in Congo Brazza, 75 carat gem octahedron was found in the 60s. And he asks if this would necessarily be a lithospheric high elevation diamond, or if it's one of these deeper.
Yeah, that's okay. So I think in the most part, when we find diamonds that are a good octahedral crystal shape, for instance, the Kimberley octahedron, which is 600 and some odd carats, it's a big octahedron. Those still appear to be part of the kind of regular population of diamonds because they have a lot of nitrogen in them, and they have this preserved crystal morphology with intact original octahedral crystal faces. So in cases where you have a nice shape of an octahedral crystal preserved, those are probably more likely to be associated with lithospheric diamond growth regions, as opposed to some of these deeper regions of growth.
All right, and actually kind of if we're on the subject of specific diamonds and specific deposits, we had a question earlier of if we expect to find type 2B diamonds at Diavik, and does it have a relationship to a subduction zone, like you mentioned with the boron being subducted down into the mantle via.
Yeah, so as far as I know, there haven't been any type 2B diamonds, these blue diamonds with boron in them. There haven't been any recovered from Canada anywhere, as far as I know. But there have been a couple of diamonds recovered from right beside beside Diavik rather, is the Acadie mine. And there's a diamond that was made headlines a few years ago, the Acadie Spirit. And more recently, there was another diamond that was 186 carats. And both of these diamonds are completely colorless and anhedral in shape. And they're actually type 2A diamonds. And they look like they probably fit into this category of clipper diamonds, even though Acadie and Diavik aren't especially known for producing diamonds like this. It looks like they probably do occur there. Now, in terms of the connection with subduction, I don't really know if they have a clear connection with deep subduction. We know that sort of more recent subduction of shallow slabs seems to have contributed saline fluids, we think, that have contributed to fibrous diamond growth. But that's something that happens within the lithosphere. So that kind of subduction story and delivery of fluids into rocks that are forming diamonds is a much shallower story. So whether or not there's some additional picture happening beneath Acadie and Diavik contributing to deeper diamond formation, I think is a open question.
Mm-hmm. Sure, because you mentioned that in order for boron to get down there, you would need, in theory, serpentinite slabs. And I don't know if there's any sort of geochemical signature that you can recognize of something that has been deeply subducted and then, I guess, recycled into a diamond to bring back up.
Yeah, yeah, and I should also point out that the idea that the boron is subducted is not proven yet. That's my
Sure.
preferred hypothesis, which I think is most likely. But if you had any kind of low degree partial melt or watery kind of fluid in the mantle, boron will partition into it. So it's not as though you can't have boron in other kinds of fluids. Mm-hmm. But as far as we know, this is these sort of super deep diamonds associated with subducted slabs seems to be the only place where type 2B diamonds have formed, as far as we can tell from the inclusions.
Mm-hmm. All right, thanks. Aaron, did you get the next question?
Well, I'm going to cheat a little bit and just ask my own, if that's okay.
Yeah.
So you said that this sort of really deep fluid release is what brings, is what's the formation mechanism for these type 2B diamonds, or that's one of the preferred theories, and that's really cool. And then with that, you use the mineral inclusions in these to say that there has to be some, there are some controls on rate of ascent of these 2B diamonds then after they're formed. But does that imply that the kimberlites are really starting at such depths as sort of this transition zone, or?
Yeah, you're getting at a question that I think is answered in this diagram by this extremely vague label here. So we've got diamond forming, and then we've got something happening here, maybe ascent or upwelling. And I've only really drawn the kimberlite starting somewhere here-ish. So the thing is, we really don't know exactly how these diamonds are transported vertically. We know the last part of the journey is in kimberlites or related volcanic eruptions, but we really don't know where kimberlites originate. There are sort of four ideas. One, that they might have something to do with a plume coming up. Two, that they might have something to do with partial melting at the base of the continental lithosphere. Maybe a third, that they might have something to do with devolatilization of these subducted slabs if they're releasing low degree carbonatitic melts. Or maybe a fourth, that they have something to do with other subducted fluids from shallower depths that are subducted maybe into the asthenosphere transition zone and aren't quite as deep as the the lower mantle. We really don't know how a kimberlite starts and whether or not that process might involve vertical transport of large materials such as these diamonds. These diamonds, some of them are fist-sized diamonds. Could the beginnings of a kimberlite be responsible for transporting those up? Maybe, but we don't really know.
And so these kimberlites, for the uneducated, which I'll include myself in, what is the general idea for how the kimberlites start?
Yeah, so I don't know if I'm the best person to give my idea, but so I think the idea is that somewhere down here towards the base of the lithosphere, you're dealing with a proto-kimberlitic kind of melt that is rich in water and it's rich in CO2. So it's almost like a carbonatitic kind of melt. And then there are chemical reactions between that melt and the continental lithosphere that involve bringing a lot of magnesium into the melt and also giving up a lot of CO2. So the melt, as it interacts with the lithosphere, is probably releasing a lot of CO2. So it's actually becoming kind of explosive, which is important for breaking up these rocks and actually generating xenoliths, but also for making this material extremely buoyant and kind of expansive so that it becomes an eruption rather than just a pocket of melt that sits here. So there needs to be some kind of release of this chemical fuel of CO2 that's stored in this low degree partial melt. But we know that it becomes very explosive at the base of the lithosphere because that's where we start seeing a lot of xenoliths that are actually entrained in the kimberlite eruption. And this, the base of the lithosphere is where the rocks are actually coherent enough that they can break and facilitate sort of focusing of a pulse of eruptive material.
Right. Great. Thanks. That was a perfect summary for me.
We have a question from earlier. Ismaila, thank you so much for your patience. You have the opportunity to ask your question now if you'd like. Oh, you're...
Okay. Thank you to ODH team. So I wanted to know about if diamond could exist as a daughter solid in fluid inclusions. I found some graphite in some fluid inclusions. If it is also carbon, I want to know if it's possible to find also diamond like daughter solid.
I don't quite understand the question. So what kind of regions?
So I want to know if it's possible to find diamond as daughter solid in fluid inclusion and other minerals.
Oh, so finding diamond as an inclusion in other minerals.
Yes.
Yes, it does occur. For instance, even at Hawaii, they have found diamonds within other minerals, but they're very, very small. So they're, maybe a micron across, like micro diamonds. Diamonds can occur within garnets sometimes, but it's very rare. Diamonds like these ones we've been talking about, for the most part, this is a fluid that's percolating between grains in a host rock. So the diamond that's growing is sort of forming after all these other mineral grains have already formed. So it's unlikely that you have a sort of a coherent mineral grain that could grow around a diamond because you don't have a lot of minerals forming after the diamonds have formed. The diamonds are sort of secondary within this existing host rock, crystallizing between those pre-existing grains.
Okay, thanks, Ismaila.
I hope that answered the question. I'm not sure.
I think, yeah, Evan, how are you feeling? Do you think you can take a few more questions? What are your
sure. Yeah, I can
energy
take some
levels?
more questions. If people have more questions, then I can do my best here.
Perfect. Yeah. Aaron, you said there's a YouTube one?
Yeah, there's actually a follow-up from Richard Redfern on YouTube, who asked the one about the Congo, the large octahedral diamond in the Congo. He cites a project where he found a small gem diamond, but it was a blue-green color that he hadn't seen before. So then Richard asks, would this color be due to boron? And he follows that with, what about the giant green diamond in the museum? Which is a little bit vague to me, but I assume not so vague to you.
Yeah, I know what he's talking about. So I maybe should have been a little bit more clear when I'm talking about
These blue diamonds being colored by boron, these are not the only diamonds that are blue or bluish green, especially when you start talking about green. You have to start talking about other causes of color. And the leading cause of color for blue or bluish greenish kinds of colors is radiation damage. So when these diamonds come to surface, they can be in contact with radioactive minerals or water that's circulating around that has radioactive particles in it. And this radioactive decay within the shallower levels at the Earth's crust can actually cause the diamond to develop these stains, radiation stains that turn it green. Or if you don't have any nitrogen in the diamond, the effect is more of a bluish color. And this is what's responsible for the color of that large green diamond in the museum. I think he's referring to the Dresden diamond, which is a really spectacular green diamond that's colored by this sort of radiation damage. So in those cases, it's not the same kind of diamond. And those diamonds are probably part of the more common population of diamonds from the lithosphere.
Thanks. Yeah, I guess I think that answers Richard's question perfectly.
And then we do have a question about what's kind of the next focus for you in terms of your research.
Yeah, I think there are hints of it here in this talk. I mean, one of the biggest things that I would like to understand better is this metallic melt that's trapped in some of these diamonds. Right now, I mean, we sort of have an idea of its bulk composition, and that's about the extent of what we know. It's difficult to get hold of samples that you can do destructive analyses on. So now we've seen that this is something that exists in many diamonds, but many of the diamonds that we're seeing it in are worth, you know, tens of thousands or millions of dollars. So we need your help now. It's an expensive problem if you really want to get great samples of it. So slowly I'm sort of trying to build up samples that it's possible to do destructive analyses on. And I would really like to understand more about how this metal phase forms and what really it means for Earth science, because it is very unusual to see samples of liquid metal just sort of hanging out in the mantle. And especially if it's associated with this sort of larger scale picture of subduction, it might be extremely important for our ideas of plate tectonic recycling and the geochemical evolution of the mantle as a whole, as opposed to just the diamond itself.
Yeah, actually, that falls in with another anonymous question we received. Magnesium-rich, super hot part of the mantle with iron, and then this molten, or this iron and nickel metals. And does this have any relationship with komatiite melt generation and things that were maybe more common sort of in the Archean?
I would say no. I'm trying to think of the connection that is being made here, but I'm not sure I understand. The magnesium-rich inclusions that we're talking about are, you know, sort of part of the most common mineral assemblage in the lower mantle. The most common mineral there is bridgmanite, and that's the magnesium silicate I'm talking about for many of these inclusions. So it's not quite as extreme as this you know, really ultramafic high degree melt that's going into komatiites. But I mean, komatiites are still an outstanding question as to how they're generated, and they probably have some connection with water in the deep mantle or extremely high temperatures in Earth's past in the mantle that could generate such a large degree of melting from deep in the Earth. So I don't see an initial connection, but yeah, I guess you never really know where the path might lead once you start examining some of these inclusions in more detail to find out their story.
Sure, I guess we're also stuck with the problem that we don't have sort of the Archean tectonic and crustal situation to look at. So we're kind of just trying to piece it together from what little bits are left on our cratons, and then I figure out how the mantle differentiation, you know, happened from that. So
Yeah,
a little bit
exactly.
different, I guess.
Limited record.
All right. Well, yeah, I think this is it. We're gonna wrap up all the questions. Thank you everybody who submitted questions, and thank you everyone who attended today. Again, thank you, Dr. Smith, for the talk and very, very enthusiastic discussion. Yeah, so just letting everyone know, we're also doing, like, of course, we're hosting another session next Wednesday, so join us. We're kind of on a diamond trend, so we're going to be hearing from Louis Chambel and about Angolan diamonds. So that'll be an interesting, I guess, follow-up to this. Aaron, do you have anything to add?
No, I just want to say join us next week for more diamond talk. Luis was here today, asked a question about Angolan diamonds, and I'm sure we'll get to learn a lot more next week. So thanks again, everybody, for joining us this evening or morning, wherever you are. And we'll see you next time.